Hi guys, I'm Nasser again. Hope you're all doing fine. Today is recording 2, and it's gonna have a little bit of an overview and history of regarding AI. And because of this, we have a great quote. We are tellers of stories, so it matches well with the history. This is from The Good Fight, by the way, season 3, episode 2. If you're familiar with Roland Blum, very interesting character. So, last time when we talked about machine learning, we were talking about there's going to be a lot of data, models, and algorithms and stuff. So to give you like a glimpse of how much data we have, actually, if you think about like an average structural or like civil engineering firm, just one of them, average size, every year they generate a lot of data. I think I found in one source this data amounts to almost 1 petabyte. So this is how many bytes it is: 1, 125, 899, 906, 842, 624. It's a massive amount of data. If you would like to print this, this would be about 500 billion pages. If you remember, floppy disks or CD-ROMs, millions and millions, of these. What I also found like a very interesting statistic was the following. Out of everything we have, we usually throw away 95% of that data. So we get to use 5%, 4% uh, of data. And if you think about this very small number of data that we use and we can do all the great things with it that we do. Imagine what would happen if we, double this data or triple this data. What we could actually do. And this is where AI is supposedly gonna help us get there, because if we can figure out what can we do with our data, we can possibly make a lot of advancements in models and such. But before we go, it's always good to pause a little bit and start to think about AI and machine learning. There are a few pieces, many pieces actually, that they have more or less this sense uh, of insinuation. The dark secret at the heart of AI is that no one really knows how the most advanced algorithms do what they do. And this could be a problem. I think this is a problem. So what we're really trying to do is we're trying to figure out how machine learning really work, because at the end of the day, we're engineers and we would like to know, these tools, how they operate, what can we do to understand them. And this could be maybe easier to visualize if you have this example here. So naturally, if we think about, failed buildings, uh, it's in blue. And if we plot the number of failed buildings between 91 and 96, we get to have this trend here. Um, if you start to plot the number of PhDs in civil engineering, it's this plot here. This is from an SF. This is from this study, from an ASA study or Dana's paper. So these are real data. So if you really look at these two trends, you see that there is a good agreement. And if you try to calculate the coefficient of linearity, you'll see that R is about 85%. That's very high correlation. That's a strong correlation, actually. Anything more than 80% is a strong correlation. So if you look at the same time frame, if you look at the failed bridges, at this trend here. If you look at the PhDs, it's the same series, so it's going to be this. If you look at the two trends, you'll see that now R is about 20%. That's a weakish correlation. So which one is it? Is it like whenever we have more PhDs, we have more failed structures, buildings, or is it or that we don't? And the storyline is actually very, very short. What we really have to look at is all data, if we can, which is hard. In these examples, we're really looking at this frame here. We have some data within some time frame, and this is what we analyze. Sometimes for some data, let's say buildings data, we have high correlation. So basically a model would work well. In this case, for bridges, different phenomena, model will struggle. It has very low correlation. at the end of the day, we really have a much more wider spectrum of data. And this is one of the things that we always have to remember with machine learning. We're gonna have different data sets. We think, we have everything, but we really don't. And the model can work as well as the data we have. So it's always a good idea to always pause and remember, like, how does this data I have on my hands and the one I'm going to be using to train models reflect on the actual data or the one we're interested in? So this is one of the slides that will have this pause thing, which tells us basically, remember, everything that looks shiny might have a different face. So when you look at the history of AI, machine learning, deep learning, it trends a little bit back, about 80 years ago and so 90, 43, 56, 65. These are very evidential cases. I mean, points in time where we have significant lapses of AI. I think I remember this. I was very young, but I remember this match when IBM's Deep Blue was playing chess. More recently, we have 2011, 2016. This is where we start to use a lot of computer vision. So algorithms no longer just use textual data, tabular data. We can use, imagery, videos, and such. Of course, it goes on and on and on, and every year has multiple things that we can think about. But this is like a very short description of these years. It always helps to see where do we come from. So in 43 there was like a small meeting in a school, and it became like a small conference, and things grew from there. So this very small conference turned out to be something that started the whole area actually, and it became very interesting. So you could go through these and read about them. Each one it probably could take us 15 to 20 minutes just to describe what we know. So I don't think this would be beneficial for these recordings, but I think it would be interesting to go back and read about those instances of time. We've seen this one before. So it's about deciding. As humans, we get to decide. Machines, unfortunately, it's going to be a little bit different for them. But at the end of the day, it always helps to see. So we know a little bit about data. We're going to come back to the data in a future chapter. We have a full chapter on the data. But when we think about machine learning, um, it always helps to see like what's actually the process, like what's the raw process, what are we trying to do? Um, what I think is one of the simplest thing to think about is the following. We have a problem or we have a phenomenon, we're trying to understand something. We come up with a hypothesis, and we say, well, based on this hypothesis and based on this problem, let's see if we can come up with some kind of model. We try theoretical models, statistical models, finite element models, numerical models, analytical models, different models. And then we eventually try to see, can we use machine learning model? And for this, we're going to have to collect some data. We're going to have to process this data. We're going to have to find an algorithm that's suitable for this problem and train this model, train this algorithm. Once you train an algorithm, it becomes a model. So a model is an algorithm with some data, because an algorithm by itself is a process that can solve things. You plug in data, it will the model transforms into a model that can solve this data. And then we evaluate the model. And if the model evaluations are great, then we're going to say, this is a good model. Let's deploy it. And deployment means we're going to be using this model now to predict, this phenomenon. And over time, we monitor it just to keep in mind. Does it perform well? Does it perform bad? Do we have new data sets that we can go back and supplement our model to make it a little better? So eventually, when we think about ML, we're really thinking about this very broadly. We're thinking about some model and some data. And when we combine both, we will be able to predict something. If we're here's where we're gonna go. Like, deep our toe is a little bit computer science, if we focus a lot on the algorithm itself, this becomes a model-centric machine learning or an algorithmic machine learning in a sub-area. If we think or focus on the data itself, it becomes a data-centric problem, so data-centric machine learning. Most of our cases actually fall here. We focus on the data itself because we apply a lot of the algorithms. If we're creating algorithms, then great, then they're going to be an algorithmic problem. Both are still within machine learning. Very good. So a good exercise would be the following. Think about a problem. Let's call it X. And, let's say that X is interesting to us. One interesting thing about them is we don't really know how X happens or how it occurs. Let's think about, I'll always revert back to my structural engineering background and I'll say, okay, well, how do beams deform? If you have a beam, horizontal member that's loaded, how would a beam, deform or deflect? Well, if you have a beam, you would like to make it deflect, you're gonna load the beam, and to measure the deflection, you're gonna have to get like an equipment or a tool to measure it. So what can we do? Well, the easiest thing would be to build a beam, take it to the lab, test it, monitor it, and observe. So we do this once, twice, three times, different beams, and we collect data. The data is important. However, whenever we do something physically, it's usually expensive. It's expensive on time, it's expensive on resources as well. Somebody would say, well, how about we go back to the literature and try to collect data from the literature? Well, that's a very good point because we have a lot of data, a lot of papers, a lot of tests. However, all these tests, most of them, they're done in different labs, different countries, different places, different beam shapes, different materials. So although we have data, it's going to be very, very hard to find like consistent data. That's basically one particular beam, one particular material, different boundary conditions, different loadings. So everything as it has, has positives and negatives. So in this case, what somebody would say, you know what, maybe the differences in beams and different labs and stuff and different equipment is not that much different. It's not substantial. We can live with those differences a little bit because we don't have resources to test 200 beams or 1,000 beams. So that's good. We collect data. And then we move to the machine learning process. Now here we're gonna have to, think of a hypothesis. What, come up with a question. How does this, how do beams fail? Well, if we go back and revert to physics, well, we have a beam because we're trying to resist loads. So because of resisting the loads, beams tend to react and then they deflect a little bit. So if you're a structural engineer, usually we like to have those load deformation curves because it tells us a lot about the beam. A load deformation curve looks like this. So you have some deformation on the x-axis, you have some loading on the y-axis, and the more you load the beam, you're gonna have some data here. Most often we have distinctive points, so you're gonna have point 1, point 2, and point 3. So if this was a concrete beam or reinforced concrete beam, point 1 is where concrete starts to crack a little bit, point 2 when steel yields, and point 3 when everything collapses. Now we knew about point 1, point 2, point 3 from watching the experiment, from observing the experiment. We've also known about this because we know concrete cracks. When you go to school, they teach you concrete cracks, steel yields. So this is where physics and domain knowledge comes in interesting. This is what we already know about the problem. Okay, so what we already know about the problem, what we observe in labs, and we're gonna try to connect these things together. So basically we have a beam. Once you load it, you're gonna have stresses, and these stresses starts to grow, and then the stresses will exceed the tensile strength of concrete cracks, stresses increase, because we're increasing the loads, then steel starts to be activated, steel will stretch, steel will yield, and so on until things collapse. So this is the behavior of one beam. What if we have two beams? We have beam 1 and beam 2. They're exactly the same, except beam 2 is a little bit shorter than beam 1. Well, logically, both of them are going to have some load deformation curves for them. Naturally, the load deformation curve for beam 2 will be a little bit shorter and smaller than beam 1 because it's the same material, same length, same span, same boundary conditions, same loading, except beam 2 is a little bit shorter. Shorter beams means they don't have enough depth to get that moment capacity high, and hence the beam will collapse much, much faster, much, much sooner. Okay, that's interesting. So this is where you can now use logic, physics and domain knowledge to figure out things. The issue becomes much more interesting when we say the following word, okay, what if we make this beam a little bit short? What if we make this loading a little bit smaller? What if we change this boundary condition? Now, as you can see, the more parameters you change or you vary, it becomes a little bit hard to connect the dots, right? It's very easy for us to figure out how things would behave if we change one parameter at a time. This is when you go, why when you do experiments, we vary one parameter at a time. Somebody could even vary two parameters and still like figure out, what's going on. Once you start to vary 3, 4, 5, 6 parameters at the same time, things become very, very complex. And this is where having data becomes a little bit interesting because if you have different data, there's potential, it potentially says or tells us that we have been seeing a lot of cases. And most likely within these cases, if you look at patterns, you can figure out things. And this is why, for instance, a senior engineer or like an experienced engineer will be able to tell you things very, very quickly because they have seen many, many instances of the same thing over and over again. So having insights would be interesting. We can get insights from observing multiple things. So this is where we can formulate like a hypothesis, and the hypothesis will tell you the following. If I'm trying to figure out the deformation in beams, I'm really trying to figure out what are the parameters that actually control this deformation, and what's the relationship between each parameter. This is what we call a governing relationship or a relationship. If I know this and I know this, I can easily predict this, whether with machine learning, with empirical methods, with anything. Unfortunately, we can always, well, this is this is the fortunate part. We can always see this in labs. We know this from physics, from domain knowledge, from our experiences. This is very hard, and this is where unfortunately this comes now a hurdle. We don't know what this is, but can we figure it out? That's a good question. So if I can figure out the governing relationships and I can get it from the parameters, then I can easily predict the deformation. Okay, so how can we find out this? Usually this is where we come up with a model. And the model would say, you know what, if you have these inputs, this would be the output. Because what a model does really, it takes the inputs and transform them into an output using, if it was a physical model using physics, if it's a simulation model using numerical analysis, and so on. From our perspective, we know that, the parameters are going to be something with geometry, height and width and depth of the beam, material properties, strength of concrete and steel, modulus, type of loading, type of boundary conditions, and so on. So as you can see, we have some information, but we don't have all the information. So if somebody would say, if this hypothesis is actually true, then I can easily figure out a lot of things because instead of deformation, I can put other ideas, other concepts. For instance, I can put creep, I can put strain, I can use cracking, I can use yielding, I can use any other phenomenon. Because as you have parameters and a governing relationship, you can figure out the output and what the output is. Okay, now let's see how machine learning how we can use machine learning to figure out this. So we have a hypothesis, we have some question on machine learning, we need a hypothesis, we're gonna have to get some data, we're gonna have to process and clean this data, we're gonna have to create a model, and so on. And this is where each chapter actually comes into play. Chapters 2, 3, 4, 5, and so on. So let's jump into some technical details. So it always helps. So the previous slides were like big ideas about this chapter, but it always helps to figure out where we are right now. If you like do a quick search on the publications in machine learning and you see something like this. So this is civil environmental engineering. So this is civil environmental, and all of these items here are civil and environmental with machine learning. So at this point in time, you can see that the publications on machine learning is about 1/3 of that, one third, maybe one fourth, one third, one fourth of all the publications in CE, which is that's a big that's a big number. You also see that the trend is rising over the past 5 years, which means there's a very good potential for it to continue to rise. So this percentage here is likely to grow with time. Interestingly, whenever there is a lot of applications on something, usually the industry follows. So you're going to see projects that use machine learning, ideas that use machine learning, communities that use machine learning. So this is why I feel this is a very good time to start to think about machine learning seriously, because the future is it's going to be very, very soon here. So other things of why machine learning is important. Well, if you learn a new method, if you think about machine learning as a new method, well, learning something new is actually something positive. It improves your understanding. Usually, we have technologies and usually they shift with time. Machine learning tends to be disruptive. It changes things very, very quickly. So learning machine learning will ensure that hopefully you are up to date. A lot of the tasks we do, if you think about design or analysis, it has a lot of repetitive component. Start process A, B, C, D. It's almost always repetitive. When something is repetitive, it's a very, very good candidate to be automated. This is what machine learning can help because we can automate a lot of things. And of course, once you automate something, you're basically make it, you can make it better and bigger. And this is where you can use it instead of, analyzing something small, you can use it for decision making, compliance, risk assessment, risk management, safety checks. It helps out with other things. But we always think start small and then when we think about machine, so the machine is the machine component. The learning component is actually the one that we have to think about. When it comes to learning, we have different ways machines or algorithms can learn. The main three at the moment, there's actually more than three, but for the sake of these slides, we have supervised learning, we have unsupervised learning. So we have one spectrum, supervised, then unsupervised, and we have something in between, semi-supervised. Supervised learning is something like this. Whenever the inputs are known, whenever the output is known, and we don't know this function that maps the input to the output. Formation. The formation would be the output. Input would be geometry, material property, but we can't figure out this from that. How to go from here to there. We can create a machine learning function or a model that we can plug in the inputs will give us the output. This would be supervised learning. So it's supervised because we are supervising. We know what the output is. We can label it. And this would be a very, very big component of a lot of things we're going to do in this textbook. Within supervised learning, we have two main things, two main concepts. We have regression. This is when the output is a number, it's regression. When the output is a class or a category, it's called classification. You're classifying something into A or B or C. Regression is there's going to be a number, a numerical value that we're going to try to predict. So supervised learning, we know inputs, we know outputs, we don't know the function. It could be regression or it could be classification. Now, unsupervised learning is a little bit interesting because for it, we know the input. We always know the input. We don't know the output here, and we don't know the function. So when we don't know the output, or when the output is not labeled, like for instance, we have a bunch of numbers and we don't know what they are. They could be deformation, they could be strength, they could be strains. This is called unsupervised. So basically the model is unsupervised and it's lit to discover what kind of data we have. And this could be something as simple as clustering. We're trying to group by behavior, call short columns together, uh, blue cars together, something like this. Dimension reduction, this is another thing that we have if you have a problem where you have too much data, a lot of parameters. Dimension reduction, it tries to figure out the most important in very, very simple terms. It will also be association. For instance, bridges that are made from eco-friendly materials tend to have lower damaging impact. Something with rules and with association. And finally, we have semi-supervised. I don't have a slide for semi-supervised, but we'll see it in the book. Semi-supervised is when the output is some of the data is labeled and some is not labeled. And here is where the model is trying to figure out the rest of the unlabeled. Now, ML itself, it also has many groups. We have black box ML, white box ML, gray box ML, we have causal ML, we also have other stuff. So black box ML, you can think of it, this is like the very big foundation. This is very coarse, very raw. We have inputs, we have output, but the model itself is the label. So basically in this case, the previous slides, we were talking about the learning process. In this slide, we're talking about the model itself. So the model is called the black box model if we don't know how it works. So the model can predict things with high accuracy, as you'll see later on, but we just don't know how it does it. How does it connect the inputs to the output? We don't know. White box model, on the contrary, is when we know. So the model still can, we plug in the inputs, it gives us the output, and we know exactly how things were predicted. In between, there's going to be a gray box. A gray box is a model that we know a little bit about it. Maybe some physics, maybe some empirical analysis can tell us something about it, but we don't know everything. Causal model is a model that can tell us this happens because of this. So it's no longer a prediction case, it's a prediction plus more information, the why of how things happen. Most of the time, we're really dealing with this, the black box model. And this is where the data-driven part comes in because we have data inputs and we have data in the output, and the model seems to predict everything from the data, and we don't know how or why. Interesting. It's very interesting because if you think about it, you have a tool, you have a model that can predict things very accurately, and you don't know how, know why. Which for some it could be it could be okay, and you don't really need to maybe. For others, you have to know. If you think about building a structure, you kind of want to know how the model works well. Otherwise, well, how do you justify decisions and stuff? For other problems, let's say, I don't know, let's say if you have an app and the app tells you, for instance, this is a picture of a certain animal. For you, it doesn't really matter how the app was able to predict the thing as long as it's correct. If you even think about the translation app, if you have like a statement you're trying to translate it, it doesn't matter to us that much how it was translated. What matters is the translation itself. So for some problems, it's okay to, I guess, not know how the model works, but for others, it's very important to know. And these would be very dependent on the situation as well. So you have to be careful. I mean, one problem for person A may not be dealt with similarly as problem, A for person B. We have to be careful of those things. So we collect data. Now we're familiar with the learning models, with the learning types of the different models. Model development is where we're here now. Model development is where we take the data, the clean data, and come up with an algorithm. And we say, well, this algorithm now is we're gonna be trained on this data using this learning process, and we're gonna come up with a model, hopefully. And we'll see this, and each one of those will have its own chapter, but in general, this is what we're trying to achieve. Now, when it comes to training a model is interesting because we're thinking about data. So how do you train a model? Well, you take an algorithm and you show it some data, and you would say something like, well, if you see, A, B, and C, predict D. If you see these numbers, this is the next number. So when it comes to training, we have a few methods. We have sampling, ratio sampling, and we have cross-validation. Ratio sampling is the easiest. So if you have a data set, you're going to say, okay, I'm going to use 70% of this data set to teach the model, the algorithm, the, to learn. This is the input and output. You show it everything, inputs and outputs for 70% of the data. Once the model is familiar with the data, and then you're going to say, okay, I'm going to take the 30% data that I haven't used in training, and I'm going to test the model. I'm going to see if the model can actually predict those unseen data. So this is what's called ratio. Ratio sampling goes between 50 to 80%. Some people push it a little bit, 50 to 90%. A good rule of thumb is to start with 70% in training and then 30 for testing, and then go from there and try to assess. So as you can see, it's a very simple process, but it could be a little bit tricky because what if the 70% you use in training, they have a lot of a specific number or a lot of one specific class. So basically, the model will not be able to know different classes. Let's say out of you have a thousand observation, 1,000 data points. You use 700 of these for training. Out of the 700, you have, I don't know, 600 class A apples and 100 class B tomatoes. And then when you train the model has seen too many apples. It hasn't seen as much as, tomatoes. So it may not be able to predict tomatoes very, very well. It may be able to over predict apples because it has seen it so much. And to overcome this item as well as other items as well, we have a different process which is usually it's much more familiar. I mean, much more common now. We have a lot of bias as you can see with sampling. The second case would be cross-validation. So cross-validation is a little bit interesting because we take all the, let's say this is our data set, this is 100%. We're going to take the training data and let's say it's 70% again. We're going to take testing data, let's say it's 30%. Out of the 70%, we're going to have false. We're going to have subsets of data. Let's say we're going to take the 70 data point and we're going to have 10 subsets. We call each subset K. So this is where the cross-validation comes in. We're going to take those K subsets and we're going to say we have 10. We're going to use 9 to train the model and we're going to keep 1 to test it. And once we finish this fold, we go to the next fold. So basically, the sampling test or fold, the one for testing, keeps changing all the time. And because of that, it's a little bit more robust. Then once we finish the training, we bring in the testing data. So it's like a multi-stage analysis for a model. And this tends to be a little bit more robust than sampling. Most of the time, K is somewhere between 5 and 15. A lot of the papers, they use 10. A good rule of thumb is, again, training data set is 7 to 30% for training with a subset, and you leave the testing set because you want to use something completely that the model hasn't seen before to train the model. Within K-fold cross-validation, we also have, stratified cross-validation. We have other things for within cross-validation. We have leave-out cross-validation. So all of these sub-items are variants of cross-validation. So basically, you could keep a subsample, leave it completely out, and do things. But the overall idea is the following. Within the data set, we have folds, and we tend to train and test within these folds. And once we finish all folds, we also tend to bring in the testing data set to test. So this is the big idea. We start with big ideas. Of course, cross-validation and sampling. What we're really trying to do is the following. We're trying to minimize a lot of model issues. For instance, we don't want the model to learn one class over the other one, or to overfit. Overfit means when the model works very, very well in training, but it doesn't work as well in testing. So when you look at the training data set, the model has high accuracy. When you look at the testing data set, it has very, very low comparative. Underfitting is the other way around, when the model doesn't work as well on training data set. Lucky guessing is basically when the model just, is lucky by guessing thing. So we're trying to minimize all of these things, because as you can see, the issue here is not really something that's physics related, or it's more about the data. And we're trying to minimize data related issues for this model. And this is where you would hear like terms like bias and variance. And I find this figure is actually interesting. So a bias is whenever you have high bias and low variance, you're gonna have underfitting. Whenever you have low bias and high variance, you're gonna have overfitting. So basically, anything that's this cross, overfitting, underfitting, is where you have high variance and high variance, low bias, low variance, high bias somewhere here. This is the most optimal case where we have things balanced. This is a very poor case where the model is just, is not performing well. So as you can see, whenever you have high variance, the predictions tend to be somehow close to the real value, but they're just spread away. When you have high bias with low variance, everything seems to be clustered up together, but it's just very, very far off the value that we need. So bias is basically the difference between the average prediction and the ground truth. The ground truth is actually the correct value or the true value. Variance is variability within the model prediction for one instance. So if you're thinking about, let's say, this particular image or this particular deformation or this particular beam, the variability within model prediction for this particular instance would give you the variance. And because you have bias and variance at the same time, this is where you have a trade-off. And the trade-off is interesting because you need to balance it. You're trying to minimize, the worst cases between the two. Yeah, there is a lot of derivation behind bias and variance. You'll find that in the board if you're like want to see the mathematical derivation for it. But overall, what the goal I'm trying to convey here is the balance. Whenever you have bias, you're gonna have variance, and balancing them becomes interesting. And balancing them is not really that. I mean, it can be. It's not very very complex now, as long as you have a healthy data set and stuff. If you have a good training process, usually models tend to be balanced somehow without much hassle. Once we build a model and once we balance it, then we have to think about, model optimization. For instance, we don't want to use models that are very, very large. They tend to be slow. If a model is also very large, if something happens to it, let's say some errors, it's going to be hard to figure out the error and how to make it, trim it down. Usually large models can be a little bit hard to maintain. They're hard to deploy because you have to have a lot of space for them to deploy them. Model management becomes a problem because you try to make it slimmer and easier to visualize, easier to use. So all of these things are more technical details that we're gonna come across, across different chapters from now on. But basically, this is the overview and history of machine learning within this recording, chapter 2. Now, if we move to the PDF a little bit, there are a few things that I would like to emphasize. What we haven't talked about so far is what is machine learning, right? What is AI? What is ML? How do you define it? Well, if you want to define ML or AI, there are many definitions and they're all interesting. Generally speaking, machine learning, we're trying to create some computer program that mimic how we learn. And the more we do something, the more they do something, the software does something, the more it becomes better at it. If you think about it, you go to school, you do one example, you you improve, you do like 10 examples or like 10 homework problems, and you become better. The more practice you do, the better we become. So this is like a philosophical way to look into machine learning and AI. If you want to think about AI itself, so John McCarthy has this very formal definition. The science and engineering of making intelligent machines, especially intelligent computer programs. It's related to the similar task of using computers to understand human intelligence, but AI does not have to confine itself to methods that are biologically observable. So simply, you are trying to have to teach a machine, a computer, a software, a process in which it analyzes data. And the more it does the process, the more it becomes a little bit more accurate. Algorithms is also something that we have to define. An algorithm is actually a method of process. So basically, it's a process that say do A, then B. If you see C, do D. If you see D, go to the next. So it's a process. It's a very unique way of saying process. So AI, machine learning, deep learning is a specific type of AI. It's mainly dealing with neural networks. So this is what deep learning is. Oh, we've talked about types of learning. I like this definition a lot, about AI machine learning. A computer program is said to learn from experience E with respect to some task, class of task or task T, and performance measure P if its performance at task in T as measured by P improves with experience E. So we have to get that experience component. The more we do something, the more we become better at. As we mentioned before, supervised learning is where we have, let's say, the inputs, all the X's, and we're trying to predict Y, and we also know Y and the label for Y. This could be regression when the output is a numeric number. And it could also be classification. But before we go, I have this learning here. Although this is self-explanatory, learning is the process of seeking knowledge, if this was something that you wanted to uh, visit. This is the figure for the famous figure for the different types with seeking these applications, classification. Here's when the output is a category, it's a class or a category, before. Unsupervised learning, we're trying to discover the underlying structure of the data or the distribution of the data. For example, if you have 5 columns or you have data on 5 columns, if you cluster them, the clustering algorithm will try to put them together, to put the columns that are most similar together somehow. Same thing with dimension reduction, PCA or association rules. Some are supervised as, when we have some outputs are labeled, some are not. We also have active learning, transfer learning, reinforcement learning, supervised, self-supervised learning. We have different types of learning. You could see that there are definitions here. Usually reinforcement is, with robots, it transfers when we create a model for one thing, but we can transfer it to other things. Self-supervised is something that's growing right now. This will be something interesting. When the model basically supervises its own learning process, rather than us doing the supervising. I don't think we have a lot of things here. A lot of philosophical items are here. A contrast between, AI and engineering, in a way. Yeah, we've discussed this. And so this Professor Hojat Ali is an Ohio State, very, very famous professor. He has a number of papers on AI. Citation 13 is a very good review paper. It's one of the first review papers actually on AI and civil engineering, CE. And in the 80s, 90s, if they didn't really use the term machine learning AI much, they use expert system. So if you're into that, historical perspective, most of the papers at that time they include expert systems versus AI in their titles, abstracts. So they may not, may not be easy to find. Mhm. Yeah, we've seen those. I'm scrolling slowly in case somebody would like to pause and read these. That might be interesting. Um, yeah, we have those. We also have these. Yeah, this might be something we could discuss. So within computational methods, we have, you might heard something that says in soft computing, hard computing. So soft computing is, basically machine learning. Hard computing is where we have, high degree of certainty. Let's say it's an algorithm or it's a process to solve things for us, but the prediction is usually with high certainty. Soft computers, they tend to be a little bit soft on the predictions. But again, black box, gray box, causal models. I've seen these. If somebody is interested, like in a PhD degree or something, causal models or physics informed models can be something interesting to go through. They're very yeah, this is one of my favorites thing about data-driven models. So this is an easy way to remember it. It's a model driven by data. So you have a model. If you change the data, the model is likely to change its prediction. This is why it's called data-driven model, not physics-driven model or I don't know, X-driven model. The model is driven by the data. So if we both of us have the same model and we use slightly different data sets, there's a very good chance that the models will not predict the same thing just because the data is different. Yeah, this is all good. I know I've said a lot of things about Phantom, but actually John Mark Francine and Thomas Journey, they have their own software, Saphir. It's like a very famous software for structural time engineering. Very good friends, brilliant software as well. Hypothesis, we've talked about this. Yeah, we've seen those. I'd like to go through the slides first and then maybe go through some of the highlights. Yeah, this would be interesting. So in the slides, we had this example, but another example that you could think about is the following. Let's say we have two beams and we're heating both beams and we have the same load. We have identical beams, different loads. So because we're heating the beams in the same way, the temperature rise in the beams will be identical. Because the loading is different, the deformation of beam 2 will be smaller than the deformation of beam 1 because the loading is small. And this is very easy to, physically relate to. If you have a smaller beam, if you have a smaller loading, the deformation will be smaller. If you have larger loading, you have larger deformation. So what would happen if, let's say, we make this fire here much more intense? What do you think the deformation will increase or will it still be the same? What would happen if the beam was a little bit longer? Just similar to what we discussed before. If you change one parameter, maybe two, we cannot can't figure out what's going to happen. But once you start change three, four, five, or six at the same time, it becomes tricky. It becomes tricky. Yeah, we've seen these formula. I've talked about databases. By the way, data is the definition for data. It's information, fact, quantity, statistics that have a purpose or a reference for analysis. This is what data is. I know this might be something very, very, very similar to. I'm sure all of you know this. Model development. Yeah, we're talking about training. We've talked about algorithms. We didn't talk about this yet. We're gonna see it soon. But usually when we build a data set, we're trying to have a balanced data set. So basically, something that has a lot of things that we expect to see in the, in reality. In reality. And for Python, I usually get questions on should I like start by learning Python or R? This is my response actually. these things are, you can think of it as a software, really. You'll find like an engineer that likes software A more than software B. Uh, it's a preference. You can, my advice is just pick one. Both are Russian will know how to use both. Fortunately, I also know how to use both. But for somebody like a new person that like to learn coding, I mean, both are very good starters. You could say if you're really looking for a sign, B happens to come before R in APC. So maybe start with Python. This is my go-to line. Yeah, we've talked about the cross validation. We've talked about overfitting, underfitting. Mm, learning bias, variance. Yeah, we covered all of those things. Yep, we've seen this one too. You'll see other terms like, for instance, hyperparameters, parameters. These are much more specific details within a model, within like an algorithm and stuff. So, uh, if I don't touch upon them here, this means we're going to cover them in a different chapter. Optimization, deployment management, yep. Conclusions. We have most of the definitions listed here too. Mm, these are good for theory questions. Yeah, so when we think about the machine learning pipeline, we usually have a problem and we try to solve it. And the question becomes, well, why use ML? What can we use theoretical analysis? Can we do tests? Can we do simulation? So my advice is try to figure out an answer to this question before you start using ML. Maybe not make ML the go-to option if not needed to, because why do you have to hassle with ML algorithms and data if you don't have to? Always remember it's an option. It's just one tool that we have that we can use. It doesn't have to we have to always use it. It doesn't mean that we have to always apply it or it will always figure out things for us. We've built many models that work out as well as theory. We built many models that work out better than theoretical model. We don't. I mean, it's a good thing to try. Hypotheses, data and processing, model development section. Okay, so we have a few questions here. Yeah, most of my questions in the early chapters were theory. I took this would be if you're teaching, yeah, I would suggest maybe go through these questions. They will help. In my class, I usually do like for instance, this one here, write 2-page paper on the history of AI, machine learning, and DL. What I normally do in my class is the following. I actually ask the students to write 1 page on the history of AI, and then I ask them to use like ChatGPT or like Bard or uh, one of those LLMs to write the other page, and then I ask them to compare the information. I find this interesting. I know every faculty have and school have their own, regulations and rules on ChatGPT like stuff. But for this course, I think it's interesting when the student compares to like their output to that from an AI output. It's a good learning process. We have citations here. So this is it for this chapter. I'm really hoping this is less than an hour. I think so. Perfect. Chapter 3. Okay, so we're gonna come back for chapter 3. And this chapter will be dedicated to data and statistics. So I'll see you soon. Thank you.